Great. Good to be here. And I want to thank especially all of the hardcore folks who are still here. I think what I'm going to try to do is pick up maybe a little bit on one of the themes that Elva just asked about, which is focused on manufacturing time series. And what I'm going to do is really share some results that come out of research that we've been doing in my group. And in particular, I'll call out Chris Lang and Damian Martin. So most of what I'm presenting is their work that has arisen from collaborations with both other students, other MIT collaborators, and in particular, an array of industrial collaborators and supporters. So ideally, what you would like in the anomaly detection is an easy and fast to deploy, relatively generic approach where you could start with almost any piece of equipment you may have for manufacturing that has some sensors or some recording data in a time series sense available, feed that through to some kind of a fault detection system and get actionable intelligence out, whether that's a fault warning, an anomaly has happened, and then as you go further, diagnostics or predictive maintenance, as we heard about yesterday, with predictions on when things are going to fail. Here again, I'm focusing on this one in anomaly detection for manufacturing data. And again, it's going to be highly multivariable data. Maybe we only have two sensor signals. I'll be showing a number of different examples, but many of them are drawn from semiconductor manufacturing, such as the ion implant signals we see up above. We have both a position as an ion beam is writing on the surface of a wafer, and we have beam current. And what we'd like to do is detect when something's gone awry. Again, these might be more multivariable. It might have 5 sensors, it might have 50, might have hundreds or thousands. And conceptually, you might plot a couple of those sensors to realize that there's correlation across sensors, but then those also trace out some kind of a trajectory in time. Many of the processes I'll be talking about here are cyclical processes. So you'll have a recording of a time series for some period of time, maybe it's a minute, and that's one run, and then we'll go to another run. And so there is a little bit of a trajectory within a cycle that we'll think of as normal, and we'll be trying to detect anomalies within that. Now, in many of the situations here, especially if you're coming into an existing manufacturing process that hopefully is working pretty well, is you may actually only have access to known good data. That is to say, you don't have a lot of examples of faults. You may, in fact, even in operation, never see the same fault more than once. And you may not, therefore, have a labeled data set. You don't have good and bad labels. Often you can assume that the past is mostly or entirely known good data. But what that suggests is that at least a good place to start is unsupervised learning. Learn from the known good data. So with that sort of as the overview or the context, unsupervised learning with only known good data, or at least that as a starting point, I'm going to try to work through, do a little bit of a deeper dive on a couple of methods. One is a fairly relatively simple approach, a Parzen window kernel method, a density estimation method. And I'll talk through a little bit the architecture, show application on this on a couple of data sets and some results. That will build to a more complicated recurrent deep auto-encoding Gaussian mixture model that sort of adds complexity, but also adds and extends some of the capability. And where I hope you find that one interesting is that it's going to actually build on many of the ingredients that you all have learned about in the last 2 days. An autoencoder architecture together with a recurrent unit, but also density estimation and a little bit of clustering. So hopefully these examples will be interesting. So to get started with the first approach, we're essentially doing what's also sometimes referred to as one-class classification, where you only have known good data. And what you'd like to do is characterize each of the good operating points in our multi-dimensional space. I'll be showing examples with 2 sensors conceptually, but again, we may have many, many more sensors with time series data. The first approach here is simplification also, in that we treat each time point independently. And this is similar to some of what we were doing early on, I think yesterday, with some of the examples that we were looking at with the disk drive data, for example. In other words, we're not explicitly considering the multiple time points jointly. We're looking and saying, is a new point of observation when we get to inference, that combination, that point in multidimensional sensor space, has it been seen before within the space of known good runs? And if so, then it's okay. If it's different, substantially different, then it's anomalous. So that's our first simplification in this approach. And what this motivates is, it goes by different names, Parzen window classifier, or some kind of a density estimation classifier. And with the Parzen window, you can imagine that each of your data points, it sort of stamps out a kernel in the multidimensional space. Maybe it's Gaussian or some other kernel that sort of says things near to that point, I want to add probability density to my space for. So as you aggregate this over known good data, you can build up a probability density map for the probability of seeing those points. And now you can imagine using this in inference, where if a new point that you observe has a probability density that's below some threshold, it's highly unlikely to have been seen, then one can classify that as faulty. Otherwise, you would assume it's good. One can extend this to multiple classes. Let's say over time you do identify some fault classes. You can also build up the probability density function for one or more faults. So this does extend to multiple dimensions, but here I'm mostly talking about sort of the one fault or the one class idea, just basic anomaly from known good data. There is conventionally, perhaps most conventionally, a kernel choice that is often used is a Gaussian function with some kind of a length scale. However, this actually can be problematic when you've got imbalance, not necessarily good, bad data imbalance, but imbalance across a cycle or across your time series for how frequently you see different combinations in the normal run cycle of those sensor signals. So the problem may be, for example, you might have a time series that's fairly continuous, as in the left, or you might have one that's sort of on the right side over here, where you've got a sharp transition. And so it's infrequent to see that sharp transition point. But now, if you do see a different sampling of that sharp transition, you might rarely see it. And that rarity might actually give you a false alarm for thinking that that's an anomalous point. To give you a little bit of a sense of this, consider a very sort of a toy example. Again, this would be two different sensors in the upper right, where we've got this sort of a Gaussian picture, where in the cycle, imagine that core of the cycle there is the normal trajectory of my sensor 1 and sensor 2. So it normally goes around that. And you build up with a Gaussian distribution around that, maybe some probability density. But at startup, right at the very sharp startup, or maybe near the end of the cycle, you might have a different combination of S1 and S2, your two sensors. So, but it's only 1 out of 1,000 time points. So it has a very low density associated with the startup. And so again, those kind of uncommon but not anomalous, low probability but not anomalous, can cause you to have false alarms. Or if you want to avoid the false alarms, you have to raise the threshold, and now you get a different trade-off of missing or detecting real alarms versus false negatives. So the approach that we actually came to after a little bit of experimentation, in fact, is to use a binary kernel. And so it's just stamping out and saying anything within some distance of a known good point is a good point. And so now you just build up the map of points you've seen before and points near enough to them. And this gets around that problem. Again, for our toy example, even that quick startup point is also a legitimate point. And it's sort of a binary, yes, I see it, I've seen it, or not, I've not seen it before. So then the question is, okay, what are you learning? What's the training step in applying one of these density function or binary kernel kinds of approaches? And the basic thing to learn is what is nearby. What do we mean by nearby? That is to say, there's some length scale or distance of similarity in sensor 1 or sensor 2, or those two sensors jointly. And so, in fact, one of the sensors, it may vary in normal operation a little bit more, as sort of pictured there in the upper right. And so I might learn for sensor 1 a longer length scale than for sensor 2. You can sort of see down here in the lower left or the lower right, we've got a good training where I might start to see, okay, this is the trajectory that I've learned between good and bad points, or I might have a bad training, which doesn't quite differentiate those and misses good points or false alarms on bad points. Another thing that we do here is ensemble training. So what we do is we take the batch, the known good data together, and now we're learning those length scales, those L sub i's associated with each of the sensors, with the minimum length scale, sort of draw the tightest boundary around those to match the data, but with cross-validation approaches being used to learn what those length scales are. So basically, we continue during learning, we'll rotate through the various data points, throwing out some of them, making sure that we still get correct labeling of those pulled out data points when they're inserted back again with the learned length scales. We're also sort of currently essentially saying for a new data point, as long as I'm near to any other known good data point, that's okay. So that's sort of a minimum distance kind of classifier here. It's been fascinating to hear a different word. I think we've heard skew sometimes referred to, but this idea of skew, temporal skew or concept drift is a real big deal. Here I'm showing some cycle index. So we'd run different cycles with a testing point density in 1,000 runs of an ion implanter. And you can see there are definite trends over periods of a few hundred cycles. And these are within the normal operating range, but they definitely move things up and down. And so especially dealing with trying to have an anomaly detection, you have to decide, are you trying to detect that drift, or are you trying to detect a really unusual point even within that drift? So we'll see a couple of approaches for this, but in this example, with our Parzen window, we found to get good results, we immediately needed to include this in our approaches. So what we do here is sort of iteratively keep learning. So this is sort of an online learning augmentation for the Parzen window, where as we get a new data point that is still close enough, it's still characterized as good because it's close enough to an existing known good data, we add that to the data set. And then to keep computational time good, but also to sort of say, way long old data points are no longer really reflective of the process, we might remove the oldest data point. So now our space of normal operation can slowly track our process. And so using that, we start to see an anomaly score. This anomaly score is basically sort of the distance or a measure of the distance to a known good point. It sort of suppresses that drift, and we get a much more stable ability to identify exceptional data points within that drift. This does come back to that question I mentioned of what kind of manufacturing control and what problem are you trying to solve. You might, in fact, be quite worried about long-term drift in your process. And so a simple approach here is actually keep track of two models. You might have the trained model based on historical known good data, and then you do that floating process along the way so that the model is tracking the drift. And then when you've got a sharp spike right there, now I can still trigger a false or a fault, an alert for a fault. But I might also maintain my earlier fixed model, not be adding or compensating for known new good data points, and watch and see when I have drifted far enough away that that model has drifted away from current behavior. Now I'd say the model has drifted so much that you might want to go back and recalibrate, retune, or reset, perhaps do periodic maintenance on that particular tool. So one of the examples I'll be showing here, and as well as in the next method, come from plasma etch in semiconductor manufacturing. This is basically a single chamber where a wafer, a silicon wafer, is placed, and an energetic plasma is generated around it with RF systems that create highly radicalized ions and species in the plasma etch. What's interesting is these are very sophisticated tools. There can be quite a large number of sensors, often 30, 40, 50 sensors on these. In this example, we focused on 5 sensors. And for the particular anomalies that we knew had been told as our test set, if you will, later from analog devices, most of those are really 2 sensors. Those that are shown here, you can see there's sort of a temperature sensor and a plasma optical intensity sensor. So there's normal operation and there's faulty operation. And what we're trying to look at is applying this Parzen window classifier to see if we could detect with just the known good data these problems. So it turns out for this, it worked fairly well. You can see here a histogram of the count of nominal data in a test set, a held out test set, and the faulty data in orange. And you can see that's measured as a distance to the training set. So sort of 1 is kind of the I'm within 1 distance measure from a known good point. And you can imagine a classifier there does a pretty good separation of these two. It's relatively easy here without tuning even of the threshold, just using that nominal 1 as the threshold. We get a false positive rate of about 1% and no false negatives. Here also, we could have gone back and modified the length scales if you want to actually tune the trade-off that we actually just heard about the cost of a false alarm versus the cost of a missed alarm. And one might move the threshold in order to reduce a false positive rate. Here's the other example that we've used for a number of cases. This is an ion implantation. So the semiconductor physics, again, is that we're doping regions of a silicon wafer. And this, again, is a cyclical process. So what we're seeing here is one cycle. And in fact, one wafer may undergo multiple cycles. And what we're seeing here is beam current, how many ions we're shooting into the surface of the wafer as a function of time. And just as example, labeled by an expert, just so we could use these for not training, but for test evaluation later. The one in the upper left is, that's a good, the green check is a nominal one. And then a couple of these X's are anomalous. And it turns out the expert knows some features to look for. Like in the lower left one, the fact that the beam current goes all the way down to 0 in this spike, that's anomalous. That's not good. Or the one in the lower right, it's very spiky. That's not good. But even the expert, by the way, has some question marks. It's not entirely clear. There are a few borderline cases that are a little bit difficult to classify. So what we wanted is, again, to apply this fairly generic approach. And what we get is something that actually has perhaps a reasonable false positive rate, but it also has a true positive rate that's reasonable, but also has some difficulties in it. And one of the things that we learned is that depending on how many known good training sets we use, if we have a large number of those known good training sets, you can imagine our space slowly of good or usual starts to grow. And so one of the challenges here is actually, if you have lots and lots of known good data, but your process actually has fairly wide operating conditions, it might become difficult because of the limitations we talked about to actually detect some of these anomalies within such a wide space of normal operation. And in fact, talking a little bit about, again, that limitation is, any distance within some known good distance of a known good point is considered good. And so if that overall space is too large, and in particular, if the time trajectory of a cycle traces out a big region, throwing away the time trace part, then you've got just really big limits, and you won't be able to detect a particular point that might have been anomalous at that time point in the cycle, given these expanded ranges. So what this suggests is, well, first off, one improvement that we've explored within this space, which is a time-dependent version. So you imagine now that depending on where we are in the cycle, you might, again, have a density distribution around what is normal behavior for that point in time across the multidimensional sensors. But really what this is a start towards a more full-bodied version of a time-dependent or time series analysis of the data, where you don't just throw away the time index, if you will, or the time sequencing, as we did in this multidimensional Parzen window example. So just applying still that Parzen window, but to that time dependence here on those two problems, you can substantially improve your true positive and your false positive rates here. But what's interesting is this is moving us towards more of the time series kind of analyses. It makes us want to consider approaches that actually look at and use jointly the time series and time correlation dependencies in addition to the multi-sensor dependencies. So you're going to see more things like the autoencoder or the LSTM coming into play in a more sophisticated approach. So what that does at this point is brings us from the simpler approach to what is what I'd call a more deep learning kind of model. And again, I'll talk about the architecture, apply it again to some of the same plasma etch data, but also to some other kinds of manufacturing data. So in this scenario, again, we're looking at anomaly detection, but now we're looking at sequences or windows of the data. Okay, so we're looking again across channels, but also across time. Is that a particular, does it have a signature across time that looks familiar or follows some dynamic behavior that a model can capture? So what we've kind of done is realize there's maybe three different kind of families of approaches for anomaly detection. We just talked about the one related to clustering or density estimation. Is it near known good clusters or perhaps near fault clusters? We also saw with sort of the autoencoder kind of idea, you might have a dimensionality reduction. That is a reconstruction, a structure that takes an input, has a smaller compressed state, and then reconstructs. And if something is different in the process, that reconstruction error will be larger. And the third is sort of a forecasting. If you have a model that can predict the next time point and it's very different from what you actually then observe, that also can be a way to signal an anomaly. And all of these, of course, depend on historical data. And there's kind of different combinations of strengths and weaknesses. So what we thought is might be interesting is take all three of these with the different elements of error or components contributing to an anomaly score, whether it's prediction error, reconstruction error from a compression, or clustering distance, and combine these together in an architecture. Combine all of those into a single measure, an anomaly measure, but be able to sort of get some of the benefits of all three approaches. So here's the architecture, and now you guys actually know how to understand or picture parts of this architecture. We called it a recurrent deep autoencoding Gaussian mixture model, in part because we've added a recurrent element to some previous DAGMM approaches. So first off, it has an autoencoder structure. It's actually a convolutional, 1D convolutional autoencoder. I should mention that actually we transform all of the input time series into a spectrum. So we transform to the frequency domain, and then we're autoencoding on the frequency spectrum. And that compresses down to a latent state. This actually is a variational autoencoder. You heard mention of that earlier. Basically, we build a model of what the mean of the latent compressed state should be, but also of what the variance should be. So we have statistics associated with the data set. So we know how unlikely or what the probability is of seeing one of those latent states. Then in that Z, that latent state from the autoencoder, that we feed to a fairly simple recurrent structure. This happens to be a gated recurrent unit. We found the simplicity of that without the long-term elements of the LSTM trained better and was a little bit simpler. Then the decode comes out and gives us a prediction of what the reconstruction would be. And that gives us, again, an error, an estimation network to look at the error between what we have seen recently and what the encoder-decoder structure predicts. And we combine that than with a classification, a clustering into different regions, sort of like we saw with the Parzen window. So it's a little bit of a kind of a neat combination. The basic autoencoder is trained with to minimize the mean square error after compression and reconstruction. You can imagine this as, creating sort of a nonlinear principal components, a nonlinear latent state. A beauty of it, again, is it's unsupervised, so we can just feed it known good data. And it also has some element, we talked about interpretability. One potential benefit is that latent state can be associated with certain important features, important sensors, but also when something is scored as an anomaly, you can sort of look back and say, which cluster was it near, or why is it far away from existing known good states? So these autoencoders in the latent states, sometimes you can structure those latent states, especially with some error functions to drive those to be orthogonal. You can get some interpretability out of these structures. I mentioned the recurrent cell. The recurrent cell is relatively simple. It's just a GRU cell, but it does also, with these short-term Fourier transform, give us some window size availability to capture some of the state dynamics for the equipment. So we combined those in one end-to-end trainable system. Again, the estimation gives us both a prediction of reconstruction error, but also predicts, is it a good example, or as you learn more, is it a bad example that goes in this diagnostic class? Then we combine all of those into an anomaly score that is essentially a negative log likelihood related to distance in the latent space, clustering in the latent space. You can imagine this model can get fairly complicated, have a lot of parameters, so we do employ implicit and explicit regularization. Some of those come just from the structure. Things like the reconstruction error helps prevent some loss. The clustering objective enforces some structure here. But we found we didn't really have to apply very much hand optimization in any way. We were able to essentially use sort of standard hyperparameters that would leave some room perhaps for some hyperparameter optimization, but we just used a standard atom with some early stopping to achieve both sort of the regularization and good training. So let me mention the data sets. Some of these you've already seen. Oops. But a new one here is both some public data sets that are available on the internet. One is a bearing data set, which I'll dive back into in just a moment. I'll show some results on milling machines, and then we'll return to our friend, the plasma etcher. So the bearing data is essentially three series of, or three kinds of time series runs, normal runs of this inner outer raceway with a ball bearing on rotating equipment, but then also some induced known faults where wear or dings on the inner raceway or the outer raceway or on the ball bearing itself were introduced. So now we have here accelerometer or vibration data. Each cycle is about 10 seconds, and we have very limited data, very important. We only have about 4 runs of each type. And one of the huge challenges, I think, for manufacturing anomaly detection is sometimes you are running the same process a small number of runs. So you'd like a method that could be employed quickly for each of your new running processes. So here's some of the results. What you're seeing here in the plot is the anomaly score on the vertical axis. And then in time, these were ordered in time, are the training data. That's the green cycles, the green runs, each of 10 seconds each. And then in red, that was the dings on the ball itself, and you can see larger anomaly scores, and similarly then for the inner or outer raceway. So here, just using 70% of the known good data of fairly small numbers of runs, although good numbers of time series by the time you are recording these at whatever it was, several kilohertz, one gets really very good, easy separation between healthy runs and these particular faulty runs. So in some sense, the bearing results is kind of too easy of a problem. In fact, we compare this with a pure variational autoencoder without even an LSTM or any other kinds of structure, or a deep Gaussian model sort of clustering approach, and they all are perfect. This is an easy problem. A somewhat harder problem is milling data. And in this case, you're milling different kinds of materials with the drill bit, and over time, the drill bit wears. You might then replace that and see if you can detect worn or non-worn mills. There's another similar data set from NASA where they actually explicitly measure the amount of wear on the tool after different kinds of runs at varying materials and feed rate and depth of cut. This is a little bit more challenging, but actually we get very good results with this architecture again. We get very good separation in the anomaly score between known good and worn tools. And you can see the anomaly score versus the run number, sort of the red. Well, on the far left, there's a small number that were the training runs, and then the other known good runs and the anomalous runs based on the known data set to see how well we actually detected does quite well. What else was interesting here is if we just use our anomaly score and plot that vertically again versus the amount of tool wear measured by NASA, there's a very strong correlation, a nice linear correlation. And this suggests that extensions where you're not just looking for an anomaly, but are looking at predictive maintenance, you'd like to be able to say, can I predict how much tool wear do I have now, and when is it going to be too much in terms of actually causing a problem? So some future hope there for predictive maintenance as an extension of this approach. The plasma etcher data, we've already seen two of the different kinds of sensor signals. Here I'm just showing more of the sensor signals for a typical cycle for one of these runs. And in this case, we actually used all 30 sensors. We didn't try to pre-screen to figure out which sensors actually matter or not. We said, those are the sensors we have, put them into the system. So we employed the RDGAMM with all 30 sensors. What else was interesting here is we had two different recipes, very different recipes running on the same tool, or the same equipment, I should say. So we have 4,000 Etcher runs. And again, the manufacturer here had historically experienced some actual faults. So here, for our testing purposes, we also knew what they had declared as bad runs and good runs. And what we find here is, again, pretty good results. The green are successful known runs per the manufacturer label, and that vertical axis is the anomaly score. So we trained on the first, I can't remember if it was first 200 runs or something like that, and then ran it on the rest of the data set. And you can see the bad data sets have big anomaly scores, easily detected in most cases. Although there are also, oops, these labels should be switched. There are a few false alarms over here a couple of the green data points that were labeled as good runs, but there's also some number of false or missed alarms, I would say, in the middle region. And a good question is sort of why that might be. Again, if we combine the two different recipes, it may be that, again, some additional work to sort of cluster out different regions of known good operating space might actually separate these a little bit better. So just combining these, sort of pulling these things, threads together, this sort of the standard or the same RDGAMM that we'd proposed across all of the data sets do quite well with detection accuracies. Usually real anomalies have anomaly scores that are much larger than the known good data. By the way, if you go back and look, these anomaly scores are actually on a log scale. So a little bit is actually orders of magnitude, large factors, larger on the anomaly scores. The encouraging thing here is we were able, in many cases, to get really good accuracy with really surprisingly little training data, which is a challenge for some of these LSTM kinds of models, but worked, or recurrent neural network models. And then inference, by the time we use that regularization and so on, we get models that are small enough to be able to be run essentially in real time or within the time of a cycle. So that's also encouraging. We do see some places where our approach is prone to some false negatives, again, on large data sets or data sets depending on the time scale. As the machine use or the space of machine use grows, accuracy decreases somewhat. There's some interesting ideas that my students have for conditioning or feeding in things like known recipe number to be able to actually condition the variational autoencoder in the middle. So there's still some room for improvement, but generally we get good results. We also think there's some nice extensions towards not just anomaly detection, but diagnosis. What is drifting and what is breaking? So if you look, one may have in different, this is one of the sensor signals on I think a plasma etch cycle. So this is one cycle on particular temperature sensing measurement. And the red is an example at week 1, and the blue is the drift of that whole trend, out in week 10, so that you can start to see the normal operation again does drift, and one can start to detect that and potentially look in the multivariate clustering space. Am I drifting from one known good towards out of range, but also towards perhaps one of these known drift areas? So we can extend the clustering idea here to also start to characterize known good faults, to diagnose particular kinds of faults. And in fact, on a couple of these data sets, we tried this idea out a little bit. We, instead of just doing sort of the one class classification, we said, okay, can the latent space, that Z variable in a autoencoder, be run through a clustering algorithm to find an appropriate number of distinct clusters? And indeed, if you remember in that bearing case, we have the normal, we have the inner raceway, outer raceway, and the ball bearing itself. And the RDGAMM with this clustering extension was able to identify 4 different clusters in that latent space and be able to achieve really good separation. And then in that plasma etch, we did the same thing. And here you see some cases where good and bad sort of overlap, meaning we couldn't perfectly separate out good runs and bad runs. But we also found over time, we could see the points drifting from a known good run, say those 945 blue, towards the 945 bad. And in some cases, you start to see some bad points relatively early. So this combination of clustering and seeing over multiple historical time how you might be drifting from one cluster to another looks like another very interesting approach to combine with these time series. So overall, lots of promise. We thought a relatively common approach, this RDGAMM, that's common or shared for many different applications, did fairly well. But I would say that the approach still leaves room for future work. There's definitely room for improvement. So just to sort of wrap up, summarize here, I tried to focus a little bit on, give you a little deeper dive on a couple of anomaly detection with manufacturing time series, starting with kind of a little bit of a simpler approach with the Parzen window density estimation, and then moved towards sort of the deep learning approach that you've gotten exposure to over the last couple of days. Out of this work and our collaboration with industrial partners, the really good news is machine learning with manufacturing time series is really feasible now. You can deploy and get great benefits. But from the university point of view, there's also still a lot of opportunities for further improvements and research, which we're very excited about. So with that, I'll wrap up and turn it back over to Bruce to MC.